Okay, so one last thing we need to talk about in this section before we go on to the next one is something called a flow line. So it's a pretty natural idea, I think. So let's imagine a scenario where we have a vector field representing a fluid by the vectors being the velocity, right? It's one of our usual points of view. And now imagine that we drop a particle into the fluid. Imagine this is a perfectly weighted, buoyant. Let's not worry about stuff like gravity and things like that. This little particle, right? Whatever direction the water is going, well, that's the direction that the particle is going to go, right? I mean, if you drop a leaf into the river, the leaf goes exactly where the water tells it to go. Okay, so we can write that down mathematically, and here it is. We've got our particle here, and if you want to talk about what is the velocity of that particle, well, the velocity of the particle, very simply, is the velocity of the fluid, right? Just as we said, the particle does exactly what the fluid tells it to do. Now, the fluid has different velocities at different locations. So when I say the velocity of the particle is the velocity of the fluid, what I mean is that the velocity of the particle is the velocity of the fluid where the particle is at the moment in question, right? So that gives us this expression right here. This is our sort of first cut at the equation. And now with that having been noted, let me just remind you, zooming back out, that the velocity of the fluid is what the vector field is, right? So that means that we can rewrite this as very simply that x prime is f of x. And this is what we call a system of differential equations. So keep in mind, position has multiple coordinates. So there's multiple coordinates in this velocity vector. And of course, the field also has multiple coordinates. So this is several equations all written in one single vector equation. It's not a single differential equation. Now, we do not yet currently know, or I should say, y'all, presuming, given the prerequisites of this course, I'm not expecting that y'all know how to solve a system of differential equations like this. This is something that will come up in Math 353. But anyway, the punchline is whatever the resulting solution is, giving position as a function of time, parameterizes what we call a flow line. Okay, so now again, I can't ask you to solve these, but I can ask you to confirm one, and that's what we're going to do in this example right here. Let's see, let me try to get, there we go. So we have a vector field given to us, and in fact, we recognize this vector field. Think back to, one of the very first vector fields we wrote down back at the start of 3.3. This was the stirred pot, right? The fluid's going around kind of counterclockwise like this. Okay, so that is our vector field, right? And as such, we have this system of differential equations. Again, don't know how to solve it, but I can ask you to confirm a solution, and I claim that this is it. I claim this cosine t comma sine t is a solution, and this is something that you can confirm directly. You plug this in and take its derivative per the left side of the equation. You plug this in into the vector field and do what the vector field says to do, namely this little formula right here. And what you will find is that the equation works. Okay. All right, so that's algebraically how you confirm that's a solution. Now, why is this a satisfying example? Why should this make you have some confidence in this equation, this big differential equation up here? Well, because we kind of know what the answer should have been, right? This is a stirred pot. The water is going around in circles. So if you drop a bay leaf into that pot, it's going to go around in a circle just like we have parameterized here. Is that good for everybody? Everybody buy it? So that's what I'm going to call a satisfying confirmation that this equation is set up right. Okay. Okay, so that finishes that section. And, one other little quick comment I want to make. This is just kind of a heads-up warning, potential landmine. A lot of students make a ill-advised choice in trying to understand vector fields, right? We've seen various examples that involve forces like gravity, like gravitational fields, electric fields. We've seen also various examples involving fluids, a stirred pot or whatever. And a lot of students might decide that they find one or the other of these to be more intuitively satisfying, something they feel a little bit more comfortable with, and then make the mistaken choice to, I'm just going to always think about vector fields in terms of fluids, or I'm going to always think about vector fields in terms of forces. I want to emphasize you can't do that. Both of these are really, really important to stuff that we're going to do later in chapter 6 and 7. There are some constructions that if you want to have any reasonable intuition for what they are and why they work, you're going to really need to be able to think of the vector field in terms of forces. And likewise, there are other constructions we're going to do that really make more sense when you think of them in terms of fluids. So don't pick one of these. Make sure that you try to develop intuition and comfort for both of these totally different physical scenarios, both being described by the same new mathematical tool, namely vector fields. Okay. All right, now we are done with 3.3 and on to 3.4. I'm going to start this with an apology. I think this is a weird time to introduce these ideas. The stuff I'm going to be telling you about in here really makes a lot more sense. It comes up much more naturally in chapters 6 and 7. So I think this is really premature. Right? Why am I going to talk about this stuff? Well, because the book does. Right? And the book is going to assume that you've seen what it has mentioned here very early in chapter 3. So I kind of feel like we have to do this. Why would the book do such a thing? Why would the book bring up stuff in chapter 3 that really doesn't fully make sense in context until chapter 6 at the earliest? And the reason is there's some pretty weird ideas in here. There's a lot going on in chapters 6 and 7. You're going to have plenty to be distracted by and thinking about and preoccupied by in chapters 6 and 7. And it's kind of nice to have just a little bit of a preview. Let some of these ideas kind of start settling in. Let you kind of start chewing on them and kind of getting used to them so that at least something will be familiar, right, when you get to chapters 6 and 7. So that's the point of view that we're going to take. I am going to go ahead and do this stuff now. But again, I have to, disclaimer, we don't really have the right tools as of yet. The claims that I'm going to make, I can't justify right now. Because to justify the claims I'm about to make, I would need to have already discussed vector line integrals and vector surface integrals and various other things that we just can't talk about just yet. So apologies, sorry, this is going to be weird and unmotivated and without context, and it is what it is. All right, so here's a familiar thing, the gradient, right? Gradient of a function. I'm going to rewrite the gradient ever so slightly like this. It's kind of the same thing. It's a little bit weird way to write it, but certainly if I were to call this this is kind of a differential operator of sorts. I'm writing it as if it's a vector. Vectors are supposed to have coordinates that are real numbers. So it's a little creepy, a little strange, but I'm going to write it like that as if that's okay. It turns out this is actually a reasonable thing to do and has a lot of important uses. The punchline then is that I can interpret that as what this symbol here means. So we're going to call this the del operator. This by itself, independent of the idea that I would apply it to a function to produce the gradient, this by itself, it turns out, is a really interesting and useful object. So we're going to be doing things now with the del operator that are not computing gradients. So along those lines, please make a point. Don't call this the gradient operator. That's a mistake. You can't call this the gradient operator. If you say the gradient operator, that would suggest two things. Both that you are talking about this object, and further, that you are talking about it being applied to something exactly in this way. And this is not the only thing that you can do with this del operator. So please don't call it gradient. That presumes too much. Okay, first thing we're going to do with the del operator. We're going to define this thing called divergence. Divergence is computed by this formula. Now, again, context. Where does this come from? Why that formula? How do I think about this? There's a bunch of stuff that's going to come up in chapters 6 and 7, in context of which this will totally make sense. Right? It'll mostly make sense. There's still some things even in chapter 6 and 7 that I'm not going to be able to talk about. This will make much more sense, though, in chapters 6 and 7. So the first thing we're going to do with the del operator is realize that it gives us kind of a nice notation for this, because check it out. Here's the del operator, and that's being applied to the coordinates one at a time of this vector field F, in the sense of first coordinate of del to first coordinate of F, second coordinate of del to second coordinate of F, third coordinate to third coordinate, and then you add them up. It's like we're doing a dot product, and thus this notation right here for divergence. So again, a lot going on here. There's a new concept called divergence. There's a formula for it, and then there's this observation that this slightly abuse of notation here actually makes a lot of sense for this formula. Okay. Now again, why are we doing this? What does this mean? What does it look like? What are we going to do with it? All that will come later. Again, apologies. The context here is no good. Okay, so all of this said, what is divergence? What is the thing that I want you all to be chewing on and kind of digesting over the next several weeks or a couple of months, or whatever it's going to be before we get to divergence? I want you all to think of divergence and the following way. It, in some sense that we will make precise later, represents how much the fluid is flowing away from wherever you're evaluating this thing called divergence. Now, let me just show you an example of what we're talking about here. I think this will be the most satisfying clarification. So here we go with an example. Here is a vector field. We've talked about this vector field before. Looks like that. Good flashback to, if you want to remind yourself where this comes from, think back to 3.3, I guess it is, the beginning of 3.3. Now let's compute its divergence and see what we get. The divergence, computed by this formula, notice that the coordinates of our vector field, wrong color. The coordinates of our vector field, x, y, and z, are what we are taking the del of. Right? So just plug it into the formula for divergence. Easy partial derivatives, and the result is 3. Okay, fine. So what that tells us then is that the divergence being 3 is positive. Reminding ourselves that divergence is supposed to be telling us, in some sense, to what extent is fluid flowing away from wherever you're evaluating. If we're thinking of this as being evaluated at the origin, then sure enough, looking at this picture of this fluid, the fluid's literally flowing away from the origin. Right? And so, to a positive extent, the divergence is telling us that the fluid is flowing away from the origin. Now, this doesn't prove anything, right? This is just an example. This shows that this interpretation at least, tracks within this example. Okay, so it's, It's a plausibility argument, I suppose you might say. It doesn't really prove anything. But this is kind of the classical picture. You know, when people say divergence, positive divergence, this should be the first picture to come to mind. So that's what we mean. How are we doing? Okay. All right. Okay, so now what does this mean physically? How would I interpret this physically? Well, there's different physical scenarios that you could imagine that this might represent. And importantly, how you interpret a positive divergence physically will depend on what kind of a physical scenario are you talking about. Roughly speaking, the point here is that not all fluids are the same kind of fluids. There are really importantly different kinds of fluids sometimes. So, first example, I like to imagine one way in which this might be the right picture. Imagine that we're in the ocean and there's a school of fish, and the fluid involved here is not the water. The fluid is the school of fish. And then out of nowhere, a shark appears right there. Right? And of course, the fish start to scatter away from the shark, of course. Right. So, okay. So, yeah, I mean, not all immediately, instantly at exactly the same time, right? In the first millisecond, some of the fish notice and start to clear out. Then a millisecond later, more fish notice and start to clear out. But slowly, actually really quickly, of course, but over milliseconds, eventually, more and more fish leave away from where the shark is. So the proposal I make of, what does this mean in this context? This means that the fish density is decreasing at that point. As it should, right? If the shark shows up, the fish density should. If you're rooting for the fish anyway, right? The fish should clear out away from where the shark is. So that's one interpretation of positive divergence. Positive divergence can mean a decreasing density of whatever fluid you're talking about. Is that all right? Does that make sense to everybody? Okay. Now, it's you might be tempted to say, but isn't that unavoidable? I mean, look, the fluid is going away. If fluid is leaving away from a general vicinity, then there's less fluid remaining. There's less fluid remaining because some of it already left. What's the scenario where that wouldn't be the case? Well, here's the other scenario, perfectly plausible scenario. Suppose that that's a light bulb. How do light bulbs work? Light bulbs generate photons. The photons then fly out like so, right? Not unlike the picture that we have drawn here. Okay? Is the density of photons decreasing? No. Light bulbs don't have photons inside of them, right? Light bulbs generate photons. They create the photons in the first place. So this need not represent a fluid that is evacuating an area. This could instead represent a fluid that's being created in that vicinity, in that area. Totally different story, right? Completely different kind of fluid, and therefore completely different interpretation of what divergence is. So I like pointing this out early. As soon as we're going to talk about divergence and what divergence looks like. Again, I think all of this is early. But as soon as we're going to talk about divergence, I think it's important to realize that there are different kinds of scenarios that are physically distinct, physically very different from each other, that give you different interpretations of what positive divergence can mean. So notice, though, that in all of these scenarios, if I can get this to cooperate, there we go. In all of these scenarios, the fluid is flowing outward away from where you are. Okay. All right. Another example. Okay, there we go. All right, another example. Let's look at this right here. We have a vector field. Now, I haven't drawn this vector field previously. I claim that this vector field looks like this. Please take a little time, however much is necessary, maybe after class if you prefer. And two things. First of all, persuade yourself that this is the right picture, pretty much. Right? But second of all, make sure you can see for yourself how you would have generated this picture. Right? It's good practice, little things like this, good practice in being able to look at some algebra, vector field algebra, and see what that means about the actual, fluid or forces or whatever the vector fields represent. Okay, so make sure you can produce that picture. That said, you can compute the divergence. The divergence is 0. That suggests that wherever I might happen to be looking, let's suppose I'm looking about right there, that general vicinity there, that there should be in the net, at least, no outward flow of fluid. And I claim that tracks, because if you look at what the fluid is doing, sure, there is some outward flow of fluid, but for every piece of fluid flowing out, there is just at the same time just as much fluid flowing in. So in the net, there's no net outward flow. So no net outward flow, no divergence. Everybody happy? Yeah.
I just wanted to ask, in the previous example, you have the del operator dot,
Yep.
the function at the zero vector. My question is
Yeah.
do you how do I say, like, input the zero vector after you do like the
when you absolutely, whenever you have a derivative and then an evaluation, you always have to do the derivative first. In fact, it's really the only thing that would make sense if you think about it. If you plug in a constant point like the origin first, then it becomes a constant. The whole expression becomes a constant, and then whatever derivatives you take would instantly be 0. And so that's rarely what we intend. So yeah, whenever the notation is written like that, it should always be assumed that you do the differentiation first, and then you plug in after.
Yeah, I just wanted to double check.
Yep.
The dot product.
Yeah, sure, absolutely. Cool. All right. Okay, here's the next new operator that we're going to talk about prematurely for various pros and cons pedagogically. This next one is called curl. Let's see, let me get into the right mode here. Curl. Curl is defined by this wacky formula right here. Now again, why? Where'd that come from? Oh my gosh, much later, right? That's going to be a long time from now. So don't look for reason, don't look for intuition on this formula itself. It is what it is, and we will put it at least into some context much later from now. Okay. Notice that this expression, being a determinant where I have standard basis vectors across the top, this is a cross product. This is that vector, which is del, cross that vector, which is, some vector field. Right? So this is a nice way to think about curl. Curl, being as it is a sort of one of these symbolic determinants, curl, this expression, is del cross F. So, nice little compact notation. And this notation, I did not make this up. This is extremely common in my past life as a second major in physics. I saw curl significantly more written like this than any other notation. It's very, very common. It's a little sketchy, right? It's a little bit of an abuse. The cross product is supposed to be just for vectors. Del is it a vector? It's a little creepy, right? But ignore that. Very compact, very convenient, very handy, very common. Okay, so again, same scenario as before. I'm about to make a completely baseless assertion here. That's where we're at. But my completely baseless assertion is that what curl represents is in some sense how the fluid is, I'm going to use this word, circulating. Very importantly, this is another thing we haven't defined yet. I haven't given you any sense of what this word circulation means. We will. We're going to be very precise about what circulation is. In Chapter 6, it's a ways off, right? Anyway, roughly speaking, circulation of fluid describes sort of a rotation of the fluid in a sense that we'll, again, be more precise about later. Now, I want to distinguish, I have examples to make this distinction. I don't mean that individual particles of fluid are rotating. And I don't mean that individual particles of fluid are traveling in round circular paths. I mean in some sense that the fluid overall has a rotation to it. So let me get to the examples that will clarify on this distinction. Specifically, before I go on, let me notice that curl is a vector because it's a cross product. And being a vector, it has two components to it. It has a direction and it has a magnitude. The direction tells me the axis that the rotation is around, and the magnitude tells me, in some sense, how much of a rotation there is around that axis. So, for example, I mean, let's suppose that the air in this room were kind of doing rotating around about like this, right? Like I'm doing with my hands. If this is the nature of the rotation, well, then the rotation of the fluid is around that axis. The curl will point in the direction of that axis that the fluid is rotating around. How much of a rotation? We're not going to set units and be precise quantifying what I mean by how much of a rotation there is, but just loosely speaking, the longer the curl vector is, the greater amount of a rotation there is, either faster or something like that. Okay. All right, so let's dive into the examples. We've seen roughly this vector field before. It's our stirred pot. This is a little different. Here I have three variables, not just x and y. Frankly, this is a little bit more representative of an honest stirred pot. Frankly, a pot is three-dimensional. Right? You cook stuff in a pot of water, that's a three-dimensional pot. So this represents that third dimension. Height is z, right? And notice that still, wherever you are, however high you are up, it's still this horizontal rotation, just like the two-dimensional example that we saw. No third component. When you stir a pot, the water is not going up or down. It's just going horizontally. Okay, so basically that's the stirred pot. So it's this picture right here. And we can compute the curl. Now this is just a matter of cranking it out, right? Let's just very, very briefly, I'll walk you through what we're talking about here. We're going to have E1 times the y partial of 0 minus the z partial of x, which gives us that 0 right there. And then we're going to have E2 times the z partial of minus y minus the x partial of 0. And that's going to give us that 0 right there. And then real quick, moving along, the E3, the x partial of x is 1. From which we subtract the y partial of minus y, which is minus 1. 1 minus minus 1 is 2. Okay, so you see all we're doing is we're basically just computing this symbolic determinant, ended up giving us this vector 0, 0, 2. Everybody with me on how that calculation went down? Okay, so the curl, this vector like that. And notice, as predicted, that gives me this vertical axis that we already knew that this fluid was rotating around. Everybody all right? All right, much more context to come in Chapter 7. Now, another example, what does it look like when there is no curl? Well, again, vector field. Again, make sure you can draw this picture looking from the algebra given for this vector field F. Make sure you can produce that this is what that vector field looks like. I'm going to make the observation that you can just see, casual glance, you can see exactly what the flow lines look like. They're like this, right? And now I'm going to make an intuitive appeal, however it might come to pass that this is what the fluid is doing, right? Nothing's rotating. Right? If I were to drop a leaf right here, the leaf would move. The leaf would start moving that way. It's not going to be rotating. Is that cool? And this tracks with the computation of the curl. You can compute the curl. You get 0, entirely consistent with the fact that that leaf is not rotating. Okay, so as we would have expected. Okay, now here's the tricky example. The tricky example comes down here. Now again, I'm just going to draw a vector field. Here's this vector field. That's what it looks like. Again, make sure that you can do this. Make sure that you can take that algebra and produce this picture. You get a bunch of arrows like this. You notice pretty quickly that all the flow lines are basically like so. They're all straight lines. They're all parallel to the x-axis. But weirdly, you compute the curl and you don't get 0. Now this is what confuses a lot of students. A lot of students say, hey, the water is all moving in straight lines. In what sense is there any rotation happening in this fluid? Well, I remind you, we're not talking about what's happening with any particular particle of fluid. We're talking about what's happening with the fluid overall. And my favorite way to kind of get at this intuitively is to think about you drop a leaf and you see, try to imagine what would the leaf do, right? And now I'm going to appeal to your sense of physical intuition that if I were to drop a leaf, let's say right there, not that it really matters. Let me zoom. If I can get this to cooperate. There you go. There's my leaf. And, well, the fluid is pushing it into the board on that side of the leaf. The fluid is pushing it out of the board on that side of the leaf. And I guess you could say those kind of oppose each other. But let me say this a little bit differently now. The fluid on this side is pushing clockwise, and the fluid over on this side is pushing it also clockwise. I think this leaf would sit there and turn. I think that this would rotate. Does that make sense? So even though no particular individual particles of fluid are seemingly have any rotational anything to them at all, as a whole, the fluid does. And that's the beautiful thing about curl. If I can get my thing to see, if my pen is too close to the thing, it won't. There we go. Curl has successfully picked up this rotation that we know would happen here. This fluid would be rotating like so. Okay, so make sure to don't misinterpret curl. Curl is not about what individual particles of fluid are doing. Curl is about what is the fluid overall doing, or said differently, if you were to drop a leaf into that fluid, if you were to drop some buoyant, perfectly weighted object, how would that thing rotate? Would that thing have a rotation in it? It's not about the fluid, it's about the stuff in the fluid. Yeah. Yeah, well, that's right. So, which way? There's an awkwardness when you say the words clockwise and counterclockwise, and I'm pretty sure I just did it myself, so I'm guilty of this as well. But if you look at my fingers, right, and if I ask you which direction are my fingers going around right now, from your point of view, it looks counterclockwise, but from my point of view, this looks clockwise, right? So there's this perspective problem. The way we distinguish that is with what we call the right-hand rule. And the right-hand rule is whichever way the rotation is happening, use your fingers of your right hand to represent that rotation, then your thumb will point in the direction of how the curl represents that motion. So in order to make my fingers do this, I have to turn my hand upside down, like so, right? Then my fingers are pointing in the direction of the rotation, and my thumb is pointing in the direction of the curl. So by this right-hand rule, this downward curl does capture the fact that this is going specifically that way. Is everybody happy with that? Okay, let's see. Where are we going now? Yeah. So you thought that was weird. Here's going to get even more weird. The stuff I showed you above is stuff that I will give you much more context for later. The stuff I'm about to show you now, I will never be able to show you at all in this course. Anyway, it turns out that the stuff that we're going to be doing in chapters 6 and 7 is the tip of the iceberg of some much deeper ideas. Ideas that mathematicians started to kind of notice, hey, wait a minute, this looks suspicious. How come here's a bunch of theorems that we keep finding that they have certain various earmarks that they're kind of related to each other, obviously, but how? What is the actual connection between these theorems? And for, I don't know the history exactly, but in the ballpark of 100 years, nobody could figure out what exactly was the connection and how do we unify, how do we see all of those as being really, truly special cases of really ultimately the same facts, the same general theorem. So very deep water to actually be able to straighten this out. And this got straightened out in the 1940s, I believe. It was the 30s or 40s. This is modern mathematics, right? This is very heavy stuff. Yeah, very recent. I know people who grew up as mathematicians with this not being knowledge on planet Earth, right? So this is very recent. Turns out, boiling off the formalities and the rigor and the abstractions and the details, the bare bones, the punchline, right? The takeaway that y'all can actually benefit from is that it turns out it really makes sense to compose the operators. In this exact specific order. So keep in mind when you take a gradient, that turns a function into a vector field. Curl then turns a vector field into another vector field. Divergence takes a vector field and then produces a real-valued function. And if you compose them in this order, just fitting the Legos together because they fit, amazing things follow. And I'm just going to show you a couple of these amazing things. There's much more than what I'm about to show you here. I'll show you more than this when we get to chapters 6 and 7. For the moment, just a little bit of a taste. Amazingly, when you compose these operators like this, everything has a lifetime of 2. It's very surprising. There is an asterisk on this. It's not technically quite everything. There's a couple of counterexamples, and they're minor and not to be worried about and not what we're here for. So let me not get distracted by that. When I say everything has a lifetime of 2, for example, if you take a gradient of a function, right? That's what we're doing down here in this algebra. We're taking a gradient, some function f. If you then subsequently take the curl of what came out of your gradient, you will always get 0 as your result. Now, why? Well, I'm going to give you a version of why on this. It's going to be a narrow, sort of like, peculiar to that particular story version. But there is a good reason for this. It makes good geometric sense. But this is just one example of this general statement of what I'm saying. All lifetimes are 2. Because what we have here is a function. I'm thinking of it as it first appeared here. So I'm going to call this birth. And it's a metaphor. It's just a metaphor. Don't overthink it. Okay? Birth, death, 2 steps later. I'm calling it a lifetime of 2. Now, there's, like I say, other versions. Here's another version of lifetimes are always 2. If I have a vector field whose divergence is 0, okay, there we have a vector field, divergence is 0. A lot of people would say, lifetime is 1. See, born here, died here, lifetime is 1. But it's not, because the theorem tells us that if your divergence is 0, then that vector field is the curl of something else. So this also is a lifetime of 2. It wasn't born here. It was born here and died there, lifetime 2. Shockingly persistent. Lifetimes are all 2. Very weird. So anyway, what can you do with this? We'll talk about it later. My point here is to try to persuade you that this composition, putting them together like this, is natural. This can't be a coincidence, right? that these shockingly convenient, consistent things always work out when you do this composition. When you do this composition, those things work out because this is actually natural. So, independent of why all this works, right? That's deep water. That's not for us. I want to persuade you that you should think of the operators as fitting together like this as we go through chapters 6 and 7 and learn about curl and divergence and some related ideas. I strongly encourage that in your mind you should be thinking of them as put together in that order. And then things will just kind of fit and things will just kind of work and everything will just kind of, you'll have a lot of good luck instead of a lot of bad luck. Yeah, did you have a...
Yeah, when you say it does that mean the operator times the vector field equals 0?
Yeah, or... I'm using 0 as my metaphor for that is death. Yeah, right. It's a dark metaphor, but, I think it works. Yeah. Okay. All right, so enough of that. As I wrote here, this is tip of the iceberg. There's a lot more connections and analogies and relationships between these operators, and we'll see all that stuff in chapter 6 and 7. Okay, so moving along. Now we just finished chapter 3. We are now going to chapter 5. What happened to chapter 4? So a couple of quick words about that. Chapter 4 is the only chapter in the book that isn't prerequisite to chapters 6 and 7. So if I could, I would move everything to after chapter 7. Chapter 6 and 7 are hard to digest. It's a lot of ideas. It just takes a lot of time for these ideas to kind of soak in and for you to just get comfortable and get intuitive sort of feeling for them. So ideally we would spend as much time on that as possible, but we can't, because I can't do chapters 6 and 7 until chapter 5, because I need chapter 5. Chapter 5 is prerequisite to 6 and 7. So is chapter 3 and 2 and 1. All of it's prerequisite except for 4. Chapter 4 is not prerequisite to 6 and 7. It's a little offshoot. It's important. It's useful. But it can wait. And it doesn't take anywhere near as much time to digest chapter 4 as it does to digest 6 and 7. So that's the idea. Chapter 4 comes last. We will get to it. We're going to dive into integrals now. And real quick, just as a reminder, when we did derivatives, I started with partial derivatives, but I made the assertion then and I think you can probably relate to it now, partial derivatives are a tool, but they're really not the protagonist in the derivative story, right? Ultimately, the big natural way to think about derivatives is as a relation between input velocities, which are vectors, and output velocities, which are vectors. And what do we do to a vector to get another vector? Matrix, right? So the big fundamentally natural, deep down, what is a derivative? What's the protagonist of the derivative story? The derivative matrix, right? You can't start with that, though. You kind of have to build your way up to it. So I gave you all a warning at the start of chapter 2. Yeah, we have to start with partial derivatives. It just it makes more sense that way, but don't hang your hat on partial derivatives as being fundamentally what derivatives are, because they're not. This is a tool. They're convenient, but they're not the story. And we're going to find exactly the same thing will happen here when we're doing integrals. I'm going to start with a certain point of view on multivariable integrals, but this that I'm about to show you is not the best way to think about it, so please take this as preliminary only. All right, and with that said, let's do a quick reminder about a fact of single variable calculus, rotated surface. Right, you want to compute the volume of a rotated surface, then you're going to look at a slice of volume, and you're going to add that up over all values of x between a and b, right? The whole is the sum of the parts. You chop up the whole volume into a bunch of little slices of volume, and the whole is the sum of the parts. And individually, any given little single piece of volume is pretty easy to compute, right? We can recognize that volume is, let's see here, there is a width. That little width is dx. And then there is a cross-sectional area. And that cross-sectional area is pi r squared, because after all, it's a disk, right? And the area of a disk, garden variety, high school geometry formula, pi r squared. And a couple of details, recognize the value of the function is the radius, and integral from a to b, right? You put it together, you get your old result about how to compute that volume. Right, does this all look familiar? Okay. All right, so I'm going to basically rip off a lot of this idea to answer a multivariable calculus question. Very different question, no rotation, but what we're going to look at is a graph of a function of two variables. Right, two variables, x and y. Kind of our domain is down here, is the xy plane. The graph is some surface up here like so. And I could reasonably ask, if I were to look over a rectangle in this domain, and if I wanted to compute the total volume under that graph, well, again, I'm trying to compute the volume of a three-dimensional thing, right? We just got through talking about how to compute the volume of a three-dimensional thing. You take slices, and the whole is the sum of the parts. Right? So we're going to rip off that same idea here. We're going to try to realize this volume as being, let me clean up the mess. This total volume, I'm going to try to recognize as being the sum of a bunch of individual parts, named little slices of volume like this, and just to have a metaphor to talk with that makes it easier to describe these things, I like to think of this as a weird-shaped loaf of bread. This is a slice of bread. Right? So the total volume of the loaf is the sum of the volumes of the slices. Right? And, okay, fine, now following along, ripping off what we did previously, we're going to look at an individual slice, and the volume of that slice is going to require understanding the thickness, which will be That's a thickness in the y direction, so that little thickness is going to be dy. And then this cross-sectional area is where we have to kind of throw up our hands, right? Because this cross-sectional area is not a disk. It's not a triangle or a rectangle or a square or a rhombus or a parallelogram. Go through the list of shapes that you learned in high school geometry. This isn't one of them. We don't know how to compute that area. So we tried to rip off this whole is the sum of the parts idea, and we've kind of hit a wall here, but there's actually a really convenient way through. Oh, and I'm out of time. Turns out there's a convenient way through this wall that we will see on tomorrow. Not tomorrow, on Friday. So see y'all on Friday. Y'all have a good one. Yeah.